because I'm not. So we will prove that this union of En, we will prove that for some n. So in particular, this is true. In particular, not D is contained in, that's not true, I'm sorry. If some function is in D, then it is in En for some n. Okay, not E is not contained in Dn. For each element of F, there is a Dn. So D is contained in union of En. N equal to 1 to infinity. Okay, this is right. Okay, is okay, no? Okay. It looks like I'm talking to myself. If someone says yes, it will be nice. Okay, so D is contained in En. Okay. D is contained in union of n equal to infinity En. Okay. Now we prove that, we claim that En is nowhere dense. That is, first, En is closed. Second, interior of En is empty. Okay, these are the two things we do. So then it is clear that D is contained in En, union of En, which is a bigger set. So D forms a first category. So it is clear. Okay. So we want to first prove En is closed. So proof of 1. Okay, we want to prove En is closed. So for each n, En is closed, and for each n, En has empty interior. En does not contain any open bar. So these are the two things we want to prove now. Okay. To prove closeness, we have to take a sequence in En, and suppose if it converges to some function f, then we have to show that this f is also in En. So let us take some Fn. I'm writing something, it's not appearing there. Okay, it has come. Let Fn be a sequence in En, and Fn converges to F. Of course, it converges in the uniform topology in C01, so in norm infinity. Okay, norm infinity. Then we want to prove, need to prove F is also En. F satisfies this condition. So that is what we want to prove. So first we want to prove En is closed. Then we want to prove it is. Then we want to prove it is nowhere dense. Okay. So Fn is in, Fn converges to F. So we want to prove that. So each Fn is in that En. That is, there exists a Xn by definition of En. En by definition, it satisfies that condition, that bounded condition. Okay, so there exists a Xn in the closed interval 0, 1, such that Fn of Xn minus f of x is less than or equal to Xn minus x n times this. Okay, this is for all Xn 0. Okay, that is how we defined. This is for all x. I forgot to say that this is for all x. Okay. The whatever you divide for the derivative, whatever the limit you take for the derivative, that is bounded by some n, natural number n. So here we are assuming, so for each n, this small n, this is true. Then we want to prove f also satisfies. For f, there exists some element for f also. That is what we want to. But the thing is, this Xn is contained in 0, 1. It is compact. So we have proved if it is compact, then it is sequentially compact. So there exists a X0 in 0, 1, such that Xn converges to X0. Right? Okay. Okay. Now we want to show that this X0 is the point we want for, is the point corresponding to this F. F satisfies that condition at this X0. So that is what we want to do. Okay. So let us just write that equation. And of course, what we will be using, there is only one thing in metric space. We will be using triangle inequality. and we use the condition that Fn converges to F, and for each Fn, it is the Xn satisfies that condition. These are the three things, and then we will use the triangle inequality. There is no other way to get an inequality in a metric space. Okay, so that is what we are going to do. So we want to prove that this x0 is the point. So we want to prove that f of x minus f of x0 is less than or equal to n times mod of x minus x0. That's what we want to prove. So we want to get to that. So for that, we want to use all the assumptions we have. Okay, so first we get f of x minus fn. I forgot to say there exists a, I mean, see, so no, you should have objected to me. I mean, I said that, xn converges to x0. It's not xn does not converge. There's only a subsequence which converges. Without loss of generality, I assume that subsequence itself is xn. Okay. I mean, it's only subsequence, but then there is no point in x and k using x and k. I use xn itself. We can do with x and k also, but for simplicity, I use xn itself. Okay, you take that as the sequence. Okay, so xn converges to x0. Okay. Okay. Now f of x minus f of x0, we want to use the triangle inequality, of course. So we write the following: f of x minus fn at x, that is what we want to, that is what we know how it get approximated, plus f of fn x minus fn x0 plus fn x0, no, fn x minus fn x0, fn x0 minus f of x0. Okay, right. Now we know that fn converges to f uniformly, so this will go to 0. You can make it less than epsilon for some n greater than something, and this will go to 0. Now you are well familiar. I mean, you are very well familiar with this argument. So this goes to 0. So we have to only worry about the middle term. So middle term is, we worry about only the middle term, which is fn x minus fn x0, which is of course less than or equal to, again, triangle inequality. We bring in the xn now, which is less than or equal to fn x minus fn of xn or xn, okay, plus fn xn minus fn x0. Here you may make a mistake. I mean, we may make a mistake because xn converges to x0 and fn is continuous. You can say that fn xn converges to fn x0, which is not true because the n is varying with the fn. Fn is also varying. Okay, so the n is fixed for any f. But then we know that these things are f. This is less than or equal to n times x minus xn plus where is x0? Yeah, n times xn minus x0. Fn minus xn minus x0. That's right. We want to write x minus x0, no, somewhere. Okay. Now xn goes to x0, so this will go to 0. So we have only x minus x0. We take limit, that will go to x0, right? And this will go to n times x minus x0. Taking limit. I mean, here there is no n, okay? And you have inequality everywhere. And you have a n everywhere. You take limit on the right-hand side, okay? On the right-hand side. So this implies taking limits. F of x minus f of x0 is this, first this term goes to this term. I underlined it, you just underline and erase it. This term goes to 0. Okay, so we can get rid of it. This term goes to 0. So we can get rid of it. Only the middle term is there. And the middle term is less than these two terms. And the one of the term goes to 0. The other term goes to x minus x0. So this is less than x minus x0. Modulus of x minus x0. Okay. This is true for all x in 0, 1. And we are, of course, using the uniform continuity. Okay, because you want to show it less than epsilon. I mean, we are somewhere using the uniform continuity. That's very important because we are using, I mean, there are two terms in the first inequality, no? You can make them together less than epsilon by that. I'm actually using that epsilon argument, but I'm just saying it converges to infinity, but you better use the epsilon argument. For example, you can make this less than epsilon by n, whatever, epsilon by 4 or something. You can make the other thing also epsilon for some big n. For the same big n or something greater than that, you can use it for the next two terms. Okay, is the argument clear? If there is some problem, if you find a problem, you tell me now. Or someone say it is clear, then I will proceed. Okay, so this implies f is in En and En is closed. Is that okay? We wanted to prove En is closed, and we did all these things, and we showed that Fn, we took a sequence in En, and we showed that if Fn converges to F, then F is also in En. Is it fine?
Yes.
Okay, no? Someone unmuted, and but it's not saying. Okay. Okay, I assume okay. If it is not okay, you tell me later. It's a very important thing to understand. So En is closed. So now we have the rest of the thing is easy. So the next proof of 2. So we want to prove that each En is nowhere dense. We have proved it is closed. So we have to prove that it does not contain any interior. Okay. So we want to prove interior of En is empty. To prove interior of En is empty. So for that we need to prove two lemma. First lemma, you consider this P01. This is all those functions in C01.
Oh.
All those continuous functions, okay, such that F is continuous, of course. So F is piecewise linear. You know what it is? P spelling, what is it? P-I or? What is the spelling of peace? Peace, not the peace, the P-E-A. Okay, let me write it. Piecewise linear. That is, there exists x1 up to xn in 0, 1. Okay. Such that, I mean, the function f is just the straight line. You know, if you, f is linear in the interval xi to xi plus 1. Of course, it is continuous. So f of the endpoint of the earlier line, the I minus 1th line and ith line should be same. So if you know f of xi, if you know f of xi plus 1, then if you know the equation of the line joining them. Okay, it's a 10th standard mathematics. You know that coordinate geometry. So it is the line. So I hope all of you know this. Okay, it's a piecewise thing. So the claim is the following. The claim is, of course, piecewise linear function. By definition, it is contained in C01, is dense. That's what you want to prove. It is dense. Proof. Okay. So given AF, we have to, given an AF and an epsilon, we have to produce some element in this P01, which is epsilon close to that in the uniform, right? That's what we want to do. So let F be some arbitrary C01 continuous function. Okay. Then we want to define this. So then F is uniform continuous. Okay. So there is given epsilon greater than 0. I mean, this epsilon is chosen. We want to find in the epsilon ball around F, we want to find a piecewise linear functional. So I take that epsilon, maybe epsilon by 2 or something. We will, I mean, maybe 2 epsilon or something. We will approximate this by approximate F by a piecewise linear functional up to 2 epsilon or something. Given epsilon greater than 0, now choose delta because it is uniformly continuous such that f of x minus f of y is less than epsilon if x minus y is less than delta. Okay. So now choose n or 1 by n less than delta. Okay. Not sorry, this is not n, small n. Okay. Small n less than delta. And define p, small p. P of xi, sorry. And xi equal to, I mean, x not equal to 0, x1 equal to 1 by n, x2, xi equal to, we go like this. Xi equal to, so x1 is 1 by n, so I by n. So we go like this, and xn, I mean, then xn equal to 1, of course. Okay. You define, that doesn't matter. We have partition so that the length is 1 by n, which is less than delta. Okay. So then define p of xi. We want to define a p. So p of xi equal to f of xi. Okay. For all I. So you know the endpoints of the line, then you know how to. Okay. So, and extend linearly. You know the endpoint of a straight line. I mean, then you know the equation of the straight line, like a line connecting them. So extend linearly. Okay. Now we want to show that this P approximate F. That's what we want to show. So to do that, we have to show that F of x minus P of x. We want to show that this is uniformly less than epsilon. That's what we want to show for all x in C0, 1. The supremum should be less than epsilon. So for all x, if this is less than epsilon, that is what we want. So let x be in, so I mean, when x is there, x is going to be in some of the interval, right? X is going to be in xi plus 1. Okay. So then this is going to be this is less than or equal to f of x minus f of xi plus f of xi minus p of x, right? Now we know that x in xi plus 1, and the distance between xi and x is less than delta. So the first term is less than epsilon. The second term, f of xi is equal to p of xi. Okay, it is p of xi minus p of x. I am saying that this is less than or equal to p of xi minus xi plus 1. Is that clear? If you take a straight line, is that clear? I mean, f of xi minus p of xi. If you take a straight line, you can parameterize it, right? If you take a point, if it is from some a to b, I mean, what I mean is a is x equal to a to x equal to b. I think, right? Then the equation of the straight line. What is the equation of the straight line? That will be b minus, let me write it. Let me see whether it is right. B minus t by b minus a times a is that point, plus y will be b minus t. When b equal to b, this vanishes, right? When no, when b equal to b, b, so t minus a it should be. I mean, if it is clear to all of you, then I will not do this, okay? T minus a times a. When a equal to t, this shouldn't vanish. When a equal to, when a, I was right earlier, I'm sorry. This will be the equation of this line, plus b minus t by b minus a. When t equal to b, that vanishes. So this will be t minus a, I think. Right? So when t equal to a, when t equal to a, this one vanishes, so it becomes a. When t equal to b, this vanishes, and that becomes b. Okay? So this is the equation of the straight line. And if you compute the distance, actual distance between the line, that will be precisely b minus t by b minus a times mod of the distance between those 2 points, actually. Okay, you do it's an exercise, okay? It's an exercise. Let me erase all these things. If you write it in the parameter sense, then you will prove that, I mean, the distance will increase. So this will be p of xi minus p of xi plus 1. Okay, I think it's, I mean, this is equal to p of xi, right? This is equal to this. And that is, this difference is less than this difference. This difference will be, it is just the distance of the line. Okay, this will be bigger. Okay. So now we know that is less than epsilon. So we know that because that is f of xi, that is equal to f of xi minus f of xi plus 1, right? This is just, I mean, p of xi equal to f of xi, p of xi plus 1 is also equal to f of xi plus 1. So these two are equal. I mean, so this is also less than epsilon. So we have proved the lemma. The lemma is proved. Shall I move to the next one, or you want to see this or discuss this or repeat some argument? Is that clear? We have proved that piecewise linear functions are dense in C01 in continuous functions. Okay, that's what we have proved. Okay. So now we prove the so I assume it's okay. So I move to the next proof. Now the proof of 2. What do you want to prove? We want to prove that it is nowhere dense. En, what we have, I recall what is En. En is equal to all those F C01 such that there exists x0 N01 such that this is comma f of x minus f of x0 the Apple Pencil is not working. So f of x minus f of x0 is less than n mod x minus x0. So we want to prove that this En is nowhere dense. We have proved it is closed. Now we have to prove that it does not contain any open ball. That is, we want to prove for any f in En and epsilon greater than 0, Okay. There exists a G in En complement such that G is in the open ball. I mean, such that G is in the open ball. So I write the condition as it is. Such that F, norm of F minus G is less than epsilon. That's what we want to prove. We take a open ball around F, epsilon open ball around F that intersects with the complement. So that is what I'm saying. G, which is not in En, G is in En complement such that F minus G is less than epsilon. That's what we want to prove. Okay, this is what we want to prove. So how do we get that? First, we will get a piecewise linear functional. Okay. So get P in piecewise linear functional, P in 0, 1, such that norm of F minus P is less than epsilon. Maybe we will get a bigger epsilon. I mean, we may have epsilon by 2 something. So given, I mean, I will change the epsilon later, okay? I mean, the radius of the ball I will change because I have to use epsilon by n or something, which I don't want to worry about, okay? So F minus P is less than epsilon. He first got a piecewise linear functional, okay? How is this piecewise linear functional will look like? So F is a curve like this. I mean, F is, of course, may not be the smooth curve, but for our convenience, we are writing like this. Then we have chosen points like this. We just crossed it like this. It's something like this, right? Okay. So we have got lines like this. A line which is, I mean, I have not written, I have not drawn the line. We have got a line, piecewise line like this, which approximates this function. Now we will get another line which approximates it, but which have a very steep thing. It goes like this. I mean, if you go have a line like this, then we go like this, steep line like this, but it doesn't go too far. Okay. What we do is the following. I will write it. I will explain you what happens. I mean, first we had F, we have F like this. Then this F is, we just had something like this, approximating it like this. Okay. Like this. Okay. Now we want to approximate that P by another line, which is like this. So we have a P like this. Okay. Then we take P plus epsilon, which will be a line like this, right? And P minus epsilon, which will be a line like this. Just epsilon distance. We start from here. I will write the equation. We start from here with a peak slope, which is greater than this n. You go and hit it like this. Once you hit, you come back with the same slope like this and go down like this. Or you can just go from here, but let me go down here. Then go like this. Okay. And when you hit it, you just come back like this. You just go on like this. Okay. You just do with a kind of, with a slope very big, we just go up and down like this. Now so for the slope, I mean it a big, let M be greater than N and Mi, where I equal to 1 to N. Where Mi's are the slopes of lines, and I mean this P contains straight lines, several straight lines, the straight lines of P. Okay, these are the slopes of Mi, and we take some M which is bigger than the original N, which is fixed for this set En, and also all this Mi. Okay, we take a big M like that. Okay. Then we define R of X. I mean, see, what I want to do is the following. I partition the interval 0, 1 so that the distance between successive points, the successive xi, yi plus 1. I mean, we already have xi for this I haven't written any xi, so it's okay. So suppose I want to find a new piecewise linear functional. For that, we have to partition the interval 0, 1. And in that partition, the successive xi and xi plus 1, I make it very small so that the slope becomes very high. So Si be a function like this. I mean, Sx, S or R, whatever I want to use. Sx equal to 0. Let us choose some, I mean, how to choose, I will tell you, okay? Choose y1 up to yn, okay? Yn, such that Sx equal to 0 if x equal to yi, okay? And it is equal to some number. I mean, same number. What is that number? Some number, some number. So let us say some h, okay? First, at the midpoint at yi plus 1 by 2, okay? At the midpoint. And I mean, I haven't chosen what is h, what is xi plus 1. Choose in such a way that the slope is m. You can do it, of course. Is there a problem in doing it? The slope is just h divided by this midpoint minus the yi, right? Which will be a number. You can make either the partition small or the h very big so that the slope will be greater than m, right? This is okay, no? This is very easy to do. Okay. Then now define. Oh no, there is another one. Sorry, why I choose like that, and this. I'm sorry. This is sorry, epsilon. This is epsilon. Sorry. I mean, S of x is epsilon. The maximum value of S is epsilon. So that the S is maximum value is epsilon. Okay. I mean, it will be it's a straight line. It takes its peak value at epsilon and comes down, of course. Now you define G equal to earlier whatever we had P and then this S. Maybe I have to put a epsilon here if you want. S epsilon. Then norm of G minus P equal to norm of S epsilon, okay, which is of course less than epsilon, right? Because which is just S epsilon, the infinity norm, which is less than epsilon. So F minus G is less than 2 epsilon. So if I change this epsilon to be 2 epsilon, so I mean all this implies B of F 2 epsilon intersection En complement is not equal to empty. This is what we want to show. Okay, we want to show that a open ball is not completely contained in En. It will intersect with the En complement. We have produced a G in En complement. I mean, why is this? I mean, why is it clear? Why? I mean, this G, this whatever, this G is not in. I hope you notice that. I write it here. G is not in En, right? Because that ratio, whatever is just the slope of the straight line. For a straight line, that is just the slope. Okay. And that slope is bigger than m. We have chosen that the slope is m. I mean, that is bigger than n. That slope is m, which is bigger than n. Slope G is not in En. So we have produced something in the complement. So which is in the open ball, which is epsilon 2 epsilon close to F. So the open ball does not intersect. I mean, it does intersect with the complement. Any doubt? We wanted to prove nowhere differentiable function forms a second category. We produced some union of En which contains the function differentiable at some point. Okay. There's a chat. Let me Would you please read? I mean, if you write it in the chat, I cannot read because I may not notice. You have to talk with me. Okay. You unmute and then you can interfere. Could you please repeat the statement that we are trying to prove? Where? You asked around 1731, 15 minutes back. I'm only seeing now. Can you ask me which one you want to repeat? Because I may not look, I don't look at the chat because I'm looking at my iPad and I don't actually notice the screen also. Okay, which argument? Oh, you know it now? You understood? Okay. We can discuss it again in the class if you want. Okay, later when I come to CMI. When I come to Chennai, we can discuss it. Okay. Anyway, let me repeat the idea. We want to prove, oh, the screen has gone.